All right, let's talk about transformations. These awesome mathematical tools that let us stretch, squish, and rotate stuff. But here's the thing, there's this special class of them called linear transformations. So, what's the big deal? What actually makes a transformation linear? Turns out it's all about following some very specific rules. And today, we're going to break them all down.
Yeah? So that's the big question, right? I mean, you see transformations everywhere, especially in things like computer graphics. All that stretching, squishing, rotating shapes on your screen. But not all of them get to be called linear. There's this exclusive club, and to get in, a function has to follow a very strict set of rules. So what are those rules?
It's actually pretty cool. It all comes down to one fundamental principle, a single golden rule, you could say, that dictates exactly how these transformations have to act. This rule is basically the dividing line between the super predictable, orderly world of linear algebra and, well, everything else. And here it is, the golden rule itself. Okay, I know that equation might look a little intense at first glance, but stick with me, because the idea behind it is actually super simple and kind of elegant. All it's saying is this: it doesn't matter if you combine your inputs first, scale them and add them together, and then do the transformation, or if you do the transformation on each input separately and then combine the results. You get the exact same answer, either way. The order just doesn't matter.
So if you break that big rule down, it's really making two core promises. First, it promises to preserve addition, meaning transforming the sum of two things is the same as summing up their transformations. Simple enough, right? And second, it promises to preserve scaling. So scaling something and then transforming it is the same as transforming it and then scaling it. It respects the basic operations. But then you have the rule breakers over on the other side. Things like just adding a constant or squaring a term. Nope, they totally shatter this beautiful, predictable structure.
Okay, so to really get what a linear transformation is doing, we gotta pop the hood and look at two really important parts. First, we need to see what stuff it completely flattens out to zero. And second, we need to see where it sends everything else. So first up is something called the kernel. You might also hear it called the null space. The easiest way to think about it is it's the collection of all the input vectors that the transformation just completely squashes down to zero. To the origin. Poof, gone. In a way, it's a measure of what information is getting lost in the process. And then you've got the other side of the coin, the range, sometimes called the image space. If the kernel is everything that gets lost or squashed to zero, the range is everything that's left. It's the complete set of all possible outputs you can get. I like to think of it as the landing zone for the transformation. It's everywhere an input vector could possibly end up. And of course, the size of these spaces is super important. The dimension of the kernel has a special name: nullity. It basically tells you how much stuff is getting flattened. And the dimension of the range? That's called the rank, and it tells you the dimension of the space that your outputs live in. Put them together, and these two numbers, rank and nullity, tell you a really deep story about the transformation. All right, so theory is one thing, but how does this work in practice? Let's get our hands dirty and run a little litmus test on an actual example. We're going to see if it can stand up to our golden rule. So here's our test subject. We've got a transformation, let's call it T, that takes a 3D vector, with components A, B, and C, and it maps it down to a 2D vector. The rule is the new vector is C, comma, A plus B. So what do you think? Is this thing linear? Let's walk through the test. So we start by taking two generic vectors, alpha and beta. We add them together first, and then we apply our transformation rule to that sum. Okay, now we do a little bit of algebraic shuffling, and look at that. The result splits perfectly into two parts. The first part is just T of alpha, and the second is T of beta. So T of the sum equals the sum of the T's. The golden rule holds. It passes with flying colors. This transformation is officially 100% linear. Okay, but let's be real. Running that formal test every single time would be a huge pain. The good news? There are some super obvious red flags, some total dead giveaways that let you spot a nonlinear imposter almost instantly. So let's look at this one here. T of x comma y equals x plus 2 comma y plus 3. Seems simple, right? All it's doing is taking a vector and just shifting it. It moves every single point 2 units to the right and 3 units up. It feels kind of orderly, but is it linear? Does it follow the golden rule? And the answer is a big, resounding nope. Not even close. See those added constants, the plus 2 and the plus 3? That is a massive red flag. Here's why. One of the core requirements for a transformation to be linear is that it has to map the 0 vector to the 0 vector. If you just shift everything, the origin moves. So that rule is instantly broken. Same thing goes for stuff like squared terms or multiplying variables together. They just don't respect the simple rules of addition and scaling. So let's dig into why that constant is such a problem. Think about it. If you add two vectors together first, and then you apply this shifting transformation, those constants get added just one time. But what if you transform each vector separately and then add them up? Well, now the +2 and +3 get added in twice, once for each of the original vectors. All of a sudden, the two sides of our equation don't match up anymore. And just like that, the golden rule is shattered. So, there you have it. You now have the tools to tell a true linear transformation from a nonlinear imposter. And this isn't just abstract math. This stuff is the absolute bedrock of fields like physics, engineering, and especially computer graphics. I mean, it's what powers everything from the 3D world in your video games to mind-bendingly complex scientific simulations. The real takeaway here is that they are predictable. They preserve structure, and that makes them incredibly powerful. Which leaves me with one final question for you. Now that you know how to spot them, where do you see these elegant, structure-preserving rules shaped